Hello, good day. For today's discussion, so we will be covering linear regression. Uh, so least squares regression, so whenever there is a substantial error that is associated with data, so polynomial interpolation is inappropriate and may yield unsatisfactory results when used to predict intermediate values. So if you could still recall, for Newton's interpolating polynomial as well as that of the Lagrange polynomial, so it resembles like this. So let's say looking at the first figure, or figure A, so shows data points, okay, so which are scattered on the x and y plane. And as you can see here, so for Newton's interpolating polynomial, so we want to create a polynomial so that would represent those data points. As such, a polynomial so should pass through all of those data points, and thus we are given a nonlinear, okay, so a nonlinear representation for those data points. However, if we are given a certain data points and then there is a linearity on the given data points, and then we want to use some prediction, okay, so we want to use some prediction, linear regression so would be best to use, especially for some predictions. And like in this particular figure, so let's say I want to determine so what would be the value of y. Okay, so let's say we are given that approximately, so x will be 8. So if I'm going to do that one, I'm just going to extend, okay, so this line, okay, or this nonlinear line, and then that is how am I going to predict, okay, so future values. However, in reality, as you can see here, so there is an increase on the slope of the data points. And if we're going to represent that one to a best fit line, so we can use a line, okay, so to represent those points, and thus we can use this line, okay, so in predicting future values, because the data points, as we can see here, so there is an increase in the value of x for every increase in the value of y. So that is why linear regressions, there are a lot of least square regression, but the most or the easiest, okay, so among those regression would be the linear regression, and that is what we will be doing, okay, so for the linear regression. So when we say linear regression, so the simplest example of least square approximation is fitting a straight line to a set of paired observations. So if we are given multiple data points, so we can use the slope-intercept form. Okay, so if you still recall in geometry, so we have this formula there, so that is y is equals to mx plus b, so which is the slope-intercept form. So where in b would serve as the intercept, and then m would correspond to the slope of the line. So the same is true for the linear regression. So we are using the same formula, but this time, so we have two variables here. So we have the a sub o and the a sub 1. So a sub 1 so would correspond to the intercept or y-intercept, and then a sub 1 would be the a sub 1 is the slope, and then a sub 0 is the y-intercept. So now, there is a derivation on how to find for the values of a sub o and a sub 1. So depending on the number of data points that we have. Okay, so the more number of data points that we have, so the more our approximation so could, or it depends. Okay, so it depends on whether we'll be able to represent the given data points into its equivalent best fit line. Okay, so A1 can be taken as n. So n here corresponds to the number of data points, and then the summation of the product of x sub I and y sub I. So x sub I so will be, so since this is summation, so that means we need to get the product of all the x and y's, and then afterwards, so we need to find the summation, and then minus the summation of the x sub I, so times the summation of y sub I, then divide it with n, the summation of x sub I squared. So we need to take the square of x sub I first, and then take the summation, and then minus the summation of x sub I squared. So we're in a sub o, so is the mean, okay, or the average for all the y's. So that means if we want to get the y bar, so that is just simply the summation of y sub I and then divide it with n. So where in n would be the number of data points. So the same is true with x bar, so that's the summation of all the x sub I divided with n. So once we were able to know what is a sub I and a sub o, so we just substitute it with our formula. So that would be the linear representation of the given data points. So let's have our first example. So that is, we are given 7 data points. So we started with 1 up to 7 for x, and then for y sub I, so it's different. So it's 0.5, 2.5, 2, 4, 3.5, 6, and 5.5. So we need to fit a straight line to the x and y values in the first two columns of the given table. So we have 1, 2, 3, 4, 5, 6, 7. So let me move that one. So this column would serve as the x sub I, and then the next one would be y sub I. And then what we need, so based on the formula that we had before, so we need to get the product of x sub I and y sub I, and then we need to square that of the x sub I. So this is 7. So we need to fill out the table first. So based on the given, so this is 0.5. We have 2.5, and then we have 2, a 4, a 3.5, a 6, and 5.5. Let me show a calculator. So we have the 1 times 0.5, so we just multiply 1 and 0.5, so that will be 0.5. 2 times 2.5, so that is 5. So 3 times 2, that is 6. Then 4 times 4, that is 16. So 5 times 3.5, so that is 17.5. Then 6 times 6 is 36. So 7 times 5.5. So that will be 38.5. And then, so we need to find what is x sub I squared. So that means, so we just square the value for x. So 1 squared is still 1. So 2 squared is 4. So 3 squared is 9. So 4 squared is 16. And then 5 squared is 25. 6 squared is 36. 7 squared is 49. So after that, so we take the summation. So the summation of x sub I, so will be, so we just add, so that is 1 plus 2 plus 3 plus 4 plus 5 plus 6 and plus 7. So which is 28. And then for y sub I, so we have 0.5 plus 2.5 plus 2 plus 4 plus 3.5 and then 6 and 5.5. So we have the summation for y sub I is 24. And then for the summation of x sub I and y sub I, so we have 0.5, so plus 5 plus 6 plus 16, 17.5, 36, and 38.5. So we have 119.5. And lastly, so we have 1 plus 4 plus 9, 16, 25, 36, and 49. So we have the summation of x sub I squared is 140. So what we want would be to find first, so what is a sub 1? So a sub 1 is the summation of, or n times the summation of x sub I, y sub I, and then minus the product of the summation of x sub I, summation of y sub I. So divide it with, so n, and then the summation of x sub I squared, then minus the summation of x sub I squared. So we can compute for a sub 1. So our n would be the number of data points. In this case, the total number of data points, so would be, so 1, 2, 3, 4, 5, 6, 7. So n here is equals to 7. So thus we have 7. And then the summation of x sub I and y sub I is this one, so which is 119.5 minus summation of x sub I is 28. Summation of y sub I is 24. So divide it with 7. So the summation of x sub I squared is this one, so which is 140. Then minus the summation of x sub I, square it, so which is 28, and then square it. So that would be, so 7 times 119.5, so minus 28 times 24, then divide it with 7 times 140, then minus 28 squared. So that's the answer. So let's try to express our answer in 8 decimal places. So 0.8392, and then we have 8571. So next is we compute for a sub o. Okay, so a sub o is y bar minus y bar minus a1 x bar. So we already have the a1. So y bar is equals to the summation of y sub I all over n, so which is 24 divided with 7. And then our x bar is the summation of xi all over n, so which is 28 all over 7, so which is equal to 4. And thus our a sub o then is equals to, so 24 over 7, so minus 0.83928571, so we multiply it with 4. So a sub 0 then, so will be 24 over 7, then minus 0.83928571 multiplied with 4. So our answer will be 0.07142,857 or 850,714,2859. Okay, so that's our y then. Base of O, so this is 0.07142859, and then our A sub 1 would be 0.83928571, and that will be our best fit line. So y is equals to 0.07142859, and then plus 0.83928571. That is why, so there is a quantification for the error of the linear regression. So remember, so let's say this one, so a sub o plus a sub 1 x sub I, so that is equivalent to the y sub I. Okay, so that is the best fit line. And then, so taking the difference of y sub I, okay, or that would be the maximum, sorry. So this should be the, or y sub I, so would be the data point, okay? So for y, and then if we're going to get the difference of the y, okay, y sub I, so minus that of the equation or the linear regression equation or function, which is the a sub o plus a sub I x sub I. So this one, so the difference between y sub I and the a sub o plus a sub 1 x sub I, so this is what we are referring as the residual. So that is the error, so that can be seen. Okay, so because we represented the data points into this regression line, okay, so into this regression line, so the discrepancy between the actual data point or the distance of the data point to that of the regression line, so that is what we are referring as the residual, or that is the error. And there is something that is a tolerable error, okay? So that means we want to achieve that one, so that tolerable error. So we can see that the closer the data points to the regression line, so the more accurate our representation, or the more accurate our best fit line or the regression line. But the farther away our data points to the regression line, so that is increases. Okay, so it increases the error that we can take, okay, so from our representation. So there are two things that we are after here. Okay, so we have the how do we represent that error? Okay, so how do we represent that error? So we have two lines actually here. So this line, so this horizontal line, so this is actually the mean line, or that is the y bar. Okay, so that's the average among the y component of the data points. So taking the average or taking the mean, so that is the mean line. So now, how far, okay, so how far the data points to the mean line, so we can quantify that one. So that is through the standard deviation. So we're in the standard deviation, so quantifies the spread around the mean. So how far, okay, so how far our data points from the mean line. And we can compute that one, the standard deviation S of y, so which is equal to the square root of the sum of the squares of the residuals around the mean line. So ST, so we need to find, okay, so the sum of the residuals from the mean line. So we can get that one, so by taking the difference So between the data point minus that of the y. Okay, so we can get that one. Okay, so I just simply the difference between the mean line. Okay, so the difference between the data points, actually the st there, so can be taken, so since it's the sum of the squares, so st is the same as the y sub I minus y bar, and then square it. Okay, so that is our st. Or sorry, that's not the st yet. So st is the summation. Okay, summation of the squares of the residual. So this is just the square of the residual. So square of the residual. S sub t is the sum of the squares of the residual. So that is how far. Okay, so how far our data points from the mean line. And then, so taking the square root, okay, so of the st divided with n minus 1. So since our data point, so we are just comparing that one to the mean line, okay, so which is y, so that is why we are just subtracting 1 here. So because our reference there is just the average, or it's just the mean, so we are taking the difference of the mean, so that's why we just have n minus 1 there. So taking that one and then take the square root, so that is the standard deviation. So the standard deviation so quantifies the spread around the mean. So how far are the data points from the mean line? So another one would be our more concern, so which is the standard error of estimate. So the standard error of estimate, or the S sub y all over x, so it quantifies the spread around the regression line. So regression line is our best fit line. So for the given data points, so how far are our data points from the regression line? So that is what we are referring as the standard error of the estimate. So this one can be taken so by taking SR. So by the way, our sum of the squares of the residuals around the regression line, so SR, so this is dependent on y sub I, so minus our y. So we're in our y is equivalent, okay, so to our formula. So y is equals to a sub 0 so this is y sub I minus y. So that means that is equal to, so y sub I, so minus a sub 0 minus a sub 1x. So a sub 0 minus a sub 1x. So as you can see here, so we are subtracting a 2 for the degrees of freedom there. So because there are two variables there, so which are, or two dependent values, so which are the a sub o and the a sub 1. So unlike on the standard deviation, so our reference there is just the mean. So in this case, it's both the a sub 0 and the a sub 1. So that's why we are subtracting it from 2. And that is the standard rate, or the standard error of the estimate. So now, so knowing the sum of the squares of the residuals around the regression line and the sum of the residuals around the mean line, so we can compute for the correlation coefficient. So but before going to compute for the correlation coefficient, so we have the coefficient of determination, which explains the percent of variability of the data. So taking the coefficient of determination, that's the r squared, so which is equal to the sum of the residuals from the mean line minus sum of the residuals from the residual line, so divided with ST. As you can see here, so we have two lines here. So for example, if for letter A, okay, so for the figure A, so So we can see that the data points are very, very close to that of the regression line. And like for the figure B, so the data points are a bit farther, okay, so from the regression line. So if we are going to compute for the sum of the residuals from the regression line, so the closer, okay, the smaller the value, okay, so the smaller the value of S sub R, so the smaller the value of S sub R, so that is how close it is, or how close will it be from the regression line. So wherein when SR is equals to 0, so that means that is the best fit line. So meaning if the data points, or if S sub R is equals to 0, so if the S sub R will be equal to 0, so that only means that the data points are very close, okay, so to the residual or to the regression line. And the regression line best describe, okay, so best describe the given data points. So when S sub R is equals to 0, that's our coefficient of determination. So if S sub R is 0, so our R squared then, so would just be ST all over ST, which is equal to 1. So that means when the coefficient of determination is 1, so that means 100% of the data, okay, so 100% of the data, so best explains, okay, so the behavior of the data points using our regression line. And then, so we have the correlation coefficient, so taking the square root, okay, or it's just the R. So the coefficient, or the correlation coefficient, especially, so if S sub R is equals to 0, so therefore our R would be equal to 1 as well. So that means a correlation coefficient of 1, so that means all the data points, okay, so the data points can be best described by the regression line. So therefore it will surely predict so future values of y, so for every values of, or for every value of x. Of course, what we want there so would be a regression, or a coefficient or correlation coefficient of 1. So anything less than that, so it could be a highly correlated, and then so it could have a correlation, so which is lessly correlated. It depends on the values of R. So we have the same example. So this time, so we're going to compute the total standard deviation, the standard error of the estimate, and the correlation coefficient, so for the data in example number 1. So we will be computing for the standard deviation. So standard deviation is SY. So standard error of the estimate, so SY all over X. And then lastly, the coefficient, correlation coefficient R. So for the data in the given example. So for us to find the standard deviation, so we need to compute first. So I'm going to copy the same data. Okay, so we need to get the residuals. So we have the y sub I minus the average, then square it. So how do we get that one? So y sub I is this one, so which is 0.5. We need to get first, so what is y bar? So y bar is 24, I guess it's 24 over 7. So it will be, so 0.5 minus 24 over 7, and then square it. So we have 8.5765 3061. Then we change that to 2.5. So it will become 0.86224489. So 90. Then so make that as 3. Oh, sorry, it should be 2. So it will be 2.048. Correct, 2.5. 0.86224,490. Then for 2, it's 2.04081633. 1633. And then so we subtract 4, that would be 0.3265. 633. 3265 3061. For 3.5, 0.00510204. Then for 6, 6.6122 4490. And then for 7, so 12, oh, sorry, 6, it's 5.5. So 4.29 081633. So we take the sum. So 8.5765 3061 was 0.8622 4490 2.0408 1633 plus 0.3265 3061 plus 0.0051 0204 plus 6.6122 4490, then plus 4.2908 1633. So the summation then, or that is the sum of the residuals from the min line. So that is 22.71428572. Okay, so to compute for the residuals, okay, so from the regression line, so we need to get, okay, so our best fit representation. By the way, this should have an X there. Okay, so we start with y sub I, so which is 0.5. Then minus 0.07142,859. And then minus 0.83928571. So we multiply it with 1, then square it. So thus we have 0.16868624. 8624. Then the next one, so our x is 2, then y is 2.5. So we have 0.56249999. And then, so we have a 3 and a 2. So 3, then we have 2. So 0.3472 5766. And then, so we have a 4 and a 4. So 0.3265 3061. And then 3.5 and 5. Or this would be 3.5, and then this is 5. So 0.5896 0459. Six and a 6. So 0.79719389. And finally, so we have an x, which is 7 and a 5.5. So 0.19929846. So getting the summation, so 0.16868624 plus 0.56249999, 0.3472 5766 plus 0.3265 3061 plus 0.5896 0459 0.79719389 and 0.19929846. So we have 2.9910 7144. So that is the sum of the residual. So to get for the standard deviation, so standard deviation is ST all over n minus 1. So that is, our ST is 22.71428572 divided with 7 minus 1. So SY, so will be the square root of 22.71428572 divided with 7 minus 1. So we have 1.94569121. Then we have the coefficient, the standard error of the estimate. So SR over n minus 2. 2.9910 7144 over 7 minus 2. So square root of 2.9910 7144 divide it with 7 minus 2. So we have 0.77344314. So that would be our SY, and this is our SY of X. Then to get the coefficient or correlation coefficient, so we get R squared first. That is ST minus SR over ST. So which is 22.71428572 minus 2.99107144 over 22.71428572. So R squared will be 22.71428572. So minus 2.99107144 divided with 22.71428572. So which is 0.8683 1761 8683 1761. So which is then, so take the square root of the answer, so giving us a correlation coefficient of 0.93183561. So which is very, very close to 1. So that means our linear regression or the regression line is the best fit for the given data points. So approximately 86.83%. Okay, so 86.83% of the data points best describes that of the regression line. And that's it. Good day.